This video, we have a liquid of a certain density of 1.65 grams per centimeters cube. It's going to flow from left to right, the left side being wider, the right side being more narrow. And the cross-section area on the left side is given as 10 centimeters square. And it said that the flow speed at this left side here is 289 centimeters per second. And the pressure on the left side here, where it's wide, is 1.2 times 10 to the 5th Pascal. And it says that the cross-section area for the narrow segment is 4 centimeters square. Part A wants us to find the speed when it flows through the narrow pipe, and then part B wants us to find the pressure of the narrow pipe, or the narrow part of the pipe. Okay. All right. So to go ahead and let's go and do this. Keep in mind when you have a horizontal pipe like this, it's important to identify your zero reference point and then measure from bottom up. Here I've drawn my reference point here in red horizontally, and then I'm just going to go up to the center of the pipe, and I'm just going to call that H1 and H2. As you can see, H1 and H2 are the same height, so according to this, height is going to be the same, and that's important to keep in mind as we set up Bernoulli's equation. Alright, the find part A, I think the easiest way to do it is just apply the continuity equation. Why? Because we have A1, we have V, we have A2, and essentially we're asked to find V2, so we're given really 3 of the 4 unknowns here. Alright, so I'm just going to go ahead and solve for V2 simply by dividing both sides by A2. Once again, A1 is given as 10 centimeters square, A2 is given as 4 centimeters square, and V1 here is given as 289 centimeters per second. So here during the Y cross-section area, V is going to be a little slower, and V, as it goes through the narrow pipe, that's going to be faster. The pressure here when V is slow is greater, so V and pressure through the pipe here is inversely related. When V is slow, pressure is high, and when V is high, pressure is going to be low. So keep that in mind as we do these numerical values. Okay. All right. So I'm going to go ahead and identify this V here on the left side, given during the Y cross-section area here is 289 centimeters per second. That's given to us, and V2 is what we're asked to find. Okay. So I'm going to go ahead and plug and chug. A1 is 10 centimeters square. V1 here is 289 centimeters per second, which is given as 12. And likewise with A2, that's given as 4 centimeters square. So really, if you simplify this on your calculator, you get a value of 722.5 centimeters per second. But I will go ahead and convert that to 7.225 meters per second if you choose to. It all depends. If the question wants in centimeters per second, stop there. If it wants in meters per second, just convert centimeters to meters. And that is your answer for this particular part A. All right, let's do part B. Part B wants us to calculate the smaller section's pressure. To do that, I know P1's given, I know the density is given, I know the two velocities now, and I know H1 and H2 are equal. So I'm going to go ahead and apply Bernoulli's equation. But here I'm going to go ahead and cross out rho GH1 and rho GH2 because H1 and H2 are equal. Because they're equal, really they end up being the same term on both sides. You can just neglect them. There's no gravitational work done here. Okay. All right. So therefore, P1 plus 1/2 rho V1 square equals P2 plus 1/2 rho V2 square. But keep in mind the question asks us to find P2. All right. So algebraically, we need to get P2 by itself, or pressure 2 here, where the cross section is small. I'm going to go ahead and do that by simply subtracting both sides by 1/2 rho V2 square. So I'm going to move this whole entire term to the left side. It's positive on the right side, so when you move it, it changes sign, so it's going to be minus. So the only difference here is I just moved that to the left side. So here is that term. Here's minus 1/2 rho V2 square. The right side has P2, and essentially that is what we're asked to find, right? We're asked to find the pressure in the narrow part of the pipe. So if you want to, you can. I'm going to. You don't have to, just so you know. I see this is 1/2 rho V1 square minus 1/2 rho V2 square. The 1/2 and the rho have, well, they appear in both these two terms, so I can factor that out. Again, you don't have to factor it out. You can just keep it as this and plug and chug. But I'm going to factor it out so I have less to plug in. So P1 gets carried down, 1/2 rho gets factored out, V1 square stays, minus sign stays, and V2 square stays. So I separate that with parentheses. Therefore, I'm just going to plug and chug. P1 is given to us 1.2 times 10 to the 5th Pascal, and then 1/2 carried down, and then the density of this particular fluid is given as 1.65 grams per centimeters cube. You notice here I highlight in black here. That's because here we have units of meters per second, but here we have grams per centimeters cubed. So you can see units don't quite match up. So make sure you pay attention to units, okay? V1, I'm just going to go ahead and plug in, that's 2.89 meters per second. The problem gives us 289 centimeters per second, but I can simply convert that to meters per second just by dividing by 100, because there's 100 centimeters for every meter. And then I already found the answer for V2 in part A. So in part A, you could have left it at 722.5 centimeters per second, but I went and converted that to meters per second. So I'm actually going to use the 7.225 meters per second because I need units to cancel out. Okay, and don't forget these V terms are being square, so make sure you carry the square down. Otherwise, you're going to goof here with just tedious work. All right. So I made a note for you here. Pay attention to units. All right. This is in meters square. That's meters square. All of a sudden, you have centimeters cubed, and this doesn't match. And Pascal is newtons over meter, right? Or meter square, excuse me, because it's force divided by area. All right. So I'm gonna go ahead and convert the 1.65 gram per centimeters cube to kilograms per meters cube, and that will equal to 1,650. So now that I have everything in meters cube, meters square, seconds, kilogram, and once again Pascal is newtons per meter square. So I can go ahead and cancel stuff out. So if you do that correctly, if you simplify your work, the 1.2 times 10 to the 5th Pascal stays, and then the 1/2 times 1,650 times negative 43.85 will give you a negative value of 36175. And this is negative because this is 2.89 square minus a bigger number square, so that's going to give you a negative number. So if you simplify this on your calculator work correctly, you should get a value of about 83,825 Pascal. Or if you want, you can convert this into scientific notation. So here I'm just going to round it about 8.38 times 10 to the 4 Pascal. Okay. And this answer seems reasonable because, once again, on the left side of the pipe, when the velocity is slow, we know the pressure is high. And the pressure started off at 1.2 times 10 to the 5th. So you notice here this is 10 to the 5th. But as it goes to the narrow part of the pipe, its speed is increasing, which implied pressure goes down. So this answer makes sense, right? I have 8.38 times 10 to the 4th power, and the 4th is less than to the 5th. So that's a reasonable answer. All right, I hope that makes sense. Stay nerdy, don't be whack.